Hello and welcome to Zetec's webinar on improving productivity and reliability for the inspection of thick carbon steel vessel welds. My name is Wayne Waxman and I'm the Director of Marketing at Zetec. I'd like to thank everyone for joining us today. I have a couple of logistical items before we get started. Everyone is in listen-only mode and we are recording today's session so you can review and listen to it or share with your colleagues in your organization. Everyone who is registered for this webinar will receive an email shortly with a link to the recording. Please note the audio or sound for this webinar will only play through computer speakers and not over the phone. Please view and listen to this webinar through your computer. Finally, there will be a Q&A session at the end of this webinar where we will be answering questions. You don't need to wait until the end of the webinar to send in a question though. If a question comes to mind at any time, simply type it in the questions section on your GoToWebinar panel. Before I turn this over to our presenter, I would like to give a quick overview of Zetec. Zetec is a global NDT leader. For nearly 50 years, we've advanced the science and standards in both ultrasonic and eddy current technologies, setting new heights in inspection performance, productivity, and predictability. Zetec's proven expertise and complete product portfolio serve the inspection needs of our customers worldwide in transportation, power generation, manufacturing, and oil and gas. Zetec is a subsidiary of Roper Technologies. Let's get to today's presentation. I'd like to introduce Guy Moss with Zetec. Guy has been involved in advanced UT method development and implementation, capability assessment, and software development for more than 25 years. Since 2000, Guy has held various positions at Zetec and RDTech, including Sales Director, Product Manager, and UT Applications Manager. Guy is currently the Sales Engineer Director, UT at Zetec. With that, I'd like to now turn this webinar over to Guy.
Thank you, Wayne. Hello, I am Guy Moss, and today I have the pleasure of presenting our solution for improving the productivity and reliability for manufacturing inspections of thick carbon steel vessel welds. This is the agenda of our webinar today. First, I will introduce the challenges encountered when performing manufacturing inspection of thick vessel welds. And then I will present the different components of the fully mechanized UT inspection system that we propose to reliably inspect such large welds. We will look at some video footage where we see the system at work in realistic conditions. This will allow me to explain to you in detail the various components of the system and the benefits they bring. After that, we will take a deeper dive in the phased array UT and TOFD inspection techniques that are deployed to achieve complete coverage of the welds and compliance with the applicable code requirements. During this part of the webinar, I will introduce several tools included in the UltraVision Classic software that are very useful for inspection technique development. By defining the inspection techniques and the required scanning sequences in detail, I will be able to accurately estimate the system performance in terms of inspection speed. After that, I will illustrate the inspection capability of the system by showing results of UT trials on representative welded specimens with realistic flaws, while demonstrating some of the advanced analysis tools in the UltraVision Classic software. And then finally, we will wrap up with some conclusions and take your questions. So let us first look at the inspection challenge. Several large carbon steel vessels are used in nuclear power plants, like the reactor pressure vessel, the steam generators, and the pressurizers. But some very similar thick wall vessels are also used in other industries. The manufacturing process of these large pressure vessels involves full volumetric non-destructive testing of the circumferential welds that connect the different segments of the vessel. Typically, these are narrow gap welds and can be up to 16 meters long and with a thickness ranging from 100 to more than 200 millimeters, or from 4 to more than 8 inches. For decades, industrial radiography, RT, complemented with manual UT, have been the commonly used examination techniques. But this inspection process has several drawbacks. RT comes with inherent radiation safety issues, and it is disruptive to other manufacturing activities, which generates overall productivity issues. Also, the complementary manual UT inspection does not produce permanent records. Over the last few years, safety regulations worldwide have become increasingly more severe, and the use of industrial radiography has been drastically restricted. At the same time, codes and standards have evolved to allow for encoded ultrasonic testing to replace radiography as the volumetric examination technique. The inspection of large vessel welds is a very specific topic, but maybe some of you will need to inspect thick carbon steel welds in other components for other industries. In that case, parts of the inspection strategy and some of the inspection techniques that I will present in the webinar may be useful for your future applications. Zetec proposes a combination of fully mechanized phased array, pulse echo, and TOFD techniques to perform the volumetric inspection of the circumferential welds in lieu of RT. And we will show in this webinar that this methodology can drastically reduce the total inspection time. The solution is intended to fulfill requirements of ASME Code Section 3 and ASME Code Section 8 for manufacturing inspections, and ASME Code Section 11 for nuclear pre-service inspections. In addition, customization to other codes or customer requirements is possible. The solution consists of a complete data acquisition system and a dedicated inspection robot that can deal with a variety of vessel diameters and a large range of wall thicknesses. The inspection is performed from the OD surface only. These are the main components of the fully mechanized UT inspection system. First of all, the laser-guided inspection robot that carries all the UT probes, then the acquisition and control unit that controls the inspection sequences and manages the recording of the examination data. And finally, the dedicated table for accurate and efficient calibration of the UT techniques. We will now take a detailed look at each of these components. The inspection robot moves along the weld on the surface of the component. It attaches to the surface by means of magnetic wheels. A linear axis allows to perform a second movement perpendicular to the weld. Different inspection sequences can be programmed. For instance, the classical raster scans or the more efficient multiple line scans parallel to the weld. The height of the linear movement allows travel over obstacles, for instance, nozzles, and the position of the legs can be adapted to move between obstacles. The tracking of the inspection robot is performed by a laser beam. The laser device can be accurately positioned and oriented, and it is mounted on the calibration table which serves as a stable mechanical reference. Two motors are used to keep the movement on track along the weld center line of the component. A probe pan containing all the probes for a given inspection sequence is attached to the linear movement. Later on in this webinar, when we are discussing the inspection techniques, we will learn more details about the type and the number of probes carried by the probe pan, but all probes are individually spring-loaded. Typically, two probe pans will be required for the inspection, one for circumferential flaws and one for axial flaws. Finally, it is important to mention that the inspection robot is supported by an automatic zero roll system. This eliminates the weight of the robot and allows for easy installation, manipulation, and removal by the operator. This slide shows a global picture and gives a summary of the various characteristics of our laser-guided inspection robot. The acquisition and control unit contains one or more dyne array systems, controlled by an industrial PC to manage the recording of the ultrasonic data. It also contains two ZMC square motor control units to support the two circumferential motors and the linear movement of the inspection robot. And finally, it includes a dedicated industrial probe connection unit to efficiently connect the elements from the various probes to the correct acquisition channels. The Zetec standard hardware and the industrial PC are mounted in a robust cabinet. The unit also offers a work surface with a large PC screen mounted on a supporting arm. This allows for a flexible orientation to fit the operator's preference, depending on his location during the calibration and inspection process. A dedicated panel allows for efficient control of the inspection flow. Its functions include coupling liquid control, coupling check during acquisition, and more. Let us now take a look at the calibration table. It has several functions. It is obviously used for UT calibration and verification during the inspection process. But as mentioned before, the embedded laser device controls the tracking of the scanner. And the calibration table supports the scanner during manipulation and inspection. In addition, it supplies and controls the coupling liquid. And finally, it is used as storage for the scanner system. In order to allow for an efficient and rapid calibration process, the complete probe pan can be easily removed from the inspection robot and installed on the calibration table. A quick connection system allows to attach the probe pan to an XY scanner integrated with the table. The calibration blocks with appropriate reference reflectors are embedded in the work surface of the table. They are used for initial calibration and characterization as well as periodic checking of the system. The manual XY scanning system allows for a manual but well-controlled and encoded movement of the complete probe pan over the calibration block surface. If required for special inspection techniques, the probe pan can also be oriented in different directions to optimize the insonification of the calibration reflectors. Coupling liquid supply and recuperation is automatically controlled. The probe pan is moved manually over the calibration block surface. A semi-automated verification procedure using the calibration tool embedded in the UltraVision Classic software allows for fast calibration checks with automated reporting, including date and time stamps. After this detailed overview of the different components of the mechanized inspection system, let us now take a deeper dive in the ultrasonic examination techniques that will be used for the full volumetric inspection of these thick vessel welds. The proposed UT methodology will be a combination of phased array UT pulse echo techniques and TOFD techniques. The wall thickness of the vessel will be divided into two depth regions, and optimized techniques will be applied in each of the zones. We will consider a near-surface region extending from 0 to 40 millimeters depth, and then we have the mid-wall and far surface region extending from 40 millimeters to the ID of the component. Pulse echo phase array UT is the primary inspection technique and is used to provide detection and sizing capability over the complete thickness range. Detection and reporting of indications will be based on amplitude level relative to a DAC curve. The detection level can be at -12 or -20 dB compared to the reference, depending on the sensitivity of the probes and the applicable code. The data acquisition system and the software allow for TCG corrections to be applied for each beam separately. Length sizing will typically be performed using the 6 dB amplitude drop technique, and where possible, backscatter tip diffraction is used for through-wall sizing. Let us start with the near-surface region. The linear electronic scanning technique is particularly suited for inspecting the region near the surface because it provides complete coverage. Obviously, we will use high angles, for instance 70-degree shear waves. The high angle will provide good specular refraction for flaws perpendicular to the surface. Let's take a look with UltraVision Classic to see how this would look like. A 1D linear array with 64 elements is shown here with a frequency of 3.5 MHz. We have chosen a focal law group performing linear electronic scanning at 70 degrees shear wave, using an active aperture of 20 elements and using the natural focusing of the probe. By looking at the different focal laws, we can observe that from a single position, this probe configuration covers a distance of approximately 40 millimeters in the index direction. To speed up the beam simulation, we will only calculate a subset of the focal laws. Let's visualize the result for a single beam first. We can observe a well-shaped acoustic beam with a lateral resolution of about 7 millimeters. By using the slider of the color palette, we can see that the sensitivity remains within 12 dB of the maximum up to a depth of 50 millimeters. And the animation shows that the beam profile is very similar for all the focal laws. Finally, by showing all simulated focal laws at the same time, we get a good idea of the global volume coverage for this position of the probe. Now let us find out what type of scanning sequence we need to make sure we cover the complete examination volume. The scanner tool in UltraVision Classic is an excellent tool to determine the type and the extent of the required scanning sequence. Starting from the same probe and law configuration that we saw before, we can now visualize the simulated scanner. Since we have learned previously that this probe configuration covers a distance of approximately 40 millimeters in the index direction, the scanner has been configured to perform a multiple line sequence, moving the probe along the weld in increments of 40 millimeters. The probe is linked to the scanner and we run a demo sequence. The region covered by the various focal laws for each scan line is visualized in blue. In order to clearly illustrate how the sequence provides actual coverage, we have added some typical welding defects to the animation. 2 lack of fusion defects in the weld bevel and a crack-like flaw in the heat-affected zone. By running the scanning sequence again, we can actually see the interaction of the focal laws with the defects. The complete examination zone is covered and each flaw is insonified on more than one scan line. From our work in ultravision, we can now conclude that the near-surface region is well covered with the linear electronic scanning at 70 degrees shear wave, in combination with the multiple line scanning sequence. Let's move to the far surface region now. To cover this region, we will use the sector scanning technique, because it provides more volume coverage at large depths. We will use a range of angles from 40 to 60 degrees shear waves. We will see later that the variety in angles will improve detection probability for specular reflection. This time we use a 1D linear array with 32 elements and a frequency of 2.25 MHz. The wedge is a standard wedge for shear wave generation. We are using the complete aperture of the probe and natural focusing. The depth zone to be covered with the beam simulation is larger, so in real time the calculation would take several minutes. Fortunately, video allows us to speed up the process. Let's first visualize the result for the individual beams and sweep from 40 to 60 degrees. The large aperture generates appropriate acoustic beams at large depth, with lateral resolution around 10 millimeters. The sensitivity remains within 12 dB of the maximum within the depth range from 100 to 200 millimeters. By showing all simulated focal laws at the same time, we confirm that there is no uncovered volume in between the individual beams. Let us now check that the multiple line scanning sequence with an increment of 40 millimeters that we proposed earlier for the near surface region can also provide adequate coverage in the far surface region. We will again use the scanner tool to find out. The probe is linked to the scanner and we run a demo sequence. A few typical welding defects have been placed in the far surface region. Lack of fusion in the weld bevel, an inclusion in the center of the weld, and a crack-like flaw in the heat-affected zone. The virtual scanning sequence confirms not only that the complete examination zone is covered, but also that each flaw is insonified with 2 or 3 different angles. This increases the detection capability of the global inspection, just like the use of several conventional UT probes with different angles. This slide now shows the summary of the ray tracing work for the far surface region, and we can conclude that the region is well covered by the sector scanning technique in combination with the multiple line scan. And finally, let's move to the mid-wall region of the weld. This part will be quite simple because we will reuse the same probes and wedges from the far surface region. We just need to add focal laws for the angles from 61 to 70 degrees to provide more coverage from 40 to 100 millimeters. For the angles between 40 and 60, the focal laws covering the far surface will also provide adequate detection in the mid-region. The image on this slide shows that each point in the examination volume is again covered by 2 or 3 different refracted angles to increase detection probability. This finalizes the detailed description of the pulse echo phased array techniques. The time of flight diffraction or TOFD technique will be used to complement the pulse echo techniques. In general, TOFD is known to be very effective for detection, characterization, and sizing of embedded flaws. It also allows for accurate through-wall sizing of far surface breaking cracks. In the specific case of thick, narrow gap welds, TOFD has additional benefits. In fact, it provides reliable detection of lack of interrun fusion defects. These are parallel to the surface of the component and a typical flaw for the narrow gap welding process. TOFD can also replace the straight beam examination that is commonly used for detection of delaminations in the base material. The proposed TOFD methodology is based on a combination of conventional TOFD using conventional UT transducers and phased array TOFD using linear phased array probes. For the near surface region from 0 to 40 millimeters depth, 2 conventional TOFD pairs at 60-degree L waves will be used. We will call this Zone 1. The 2 pairs each have an offset relative to the weld center line. This is done to achieve complete coverage of the weld and the heat effective zone as shown in this animation. For the midwall and the far surface region from 40 to 200 millimeters depth, it would take at least 3 additional conventional TOFD pairs, each with a specific probe center separation and refracted angle. This would become quite complicated for the probe pen design. This is why we decided to apply phased array TOFD. A single pair of 1D linear phased array probes at a fixed probe center separation will be used to generate 3 TOFD configurations at various angles to cover the complete depth extent. Obviously, like for conventional TOFD, longitudinal or L waves will be used. The next animation shows how the TOFD inspection coverage assessment is performed using the TOFD configuration tool in the UltraVision Advanced Phased Array Calculator. Like for pulse echo phased array, we will be tolerating 12 dB as the maximum sensitivity reduction over the covered zone. In Zone 4, the region closest to the far surface, a TOFD pair with nominal beam angle of 40 degrees is generated. The actual coverage is shown in red. For Zone 3, closer to midwall, a TOFD focal law with nominal beam angle around 45 degrees is used. The 12 dB coverage shown in green. And finally, a TOFD configuration with a nominal beam angle of roughly 60 degrees is used to get coverage in Zone 2, up to 40 millimeters under the near surface. The global coverage is then indicated by the black rectangle, and we can observe that its extent is larger than 40 millimeters. So if the code required examination volume is larger than 40 millimeters, a multiple line scanning sequence with mechanical increments of typically 40 millimeters will allow us to achieve complete coverage. The coverage of the phased array TOF techniques can also be verified by calculating the actual acoustic field generated by a given TOF focal law in Ultravision Classic. Let's take zone 3 as an example and start from the coverage found with the TOF configuration tool. We will now compare with the result from the acoustic beam simulation limited to the zone where the amplitude drop is 12 dB or less. We can see a pretty good match between the simple geometrical result and the calculation of the acoustic field. Obviously, this confirmation inspires confidence in the result, but still, experimental validation with actual probes on test specimens with appropriate reflectors is recommended. This concludes the technique development for the TOF technique. Now that we have determined the key parameters for all individual inspection techniques, it is time to summarize the different probe assemblies that we will deploy on the thick vessel weld. First of all, two linear array probes with 64 elements at a frequency of 3.5 MHz will cover the near surface region using electronic linear scanning. Next, we have two additional linear array probes with 32 elements at 2.25 MHz to cover the remainder of the volume using sectorial scanning. We will have two conventional TOF pairs for complementary coverage of the near surface region. And finally, a single TOF pair with 2 × 16 elements linear array probes at 5 MHz for complementary coverage of the remaining depth. In order to perform a rapid and efficient inspection, we want to run all the probes simultaneously. So as mentioned before, the probes will be mounted on a single probe pan carried by the laser-guided inspection robot. But this also means that we need a phased array system with at least 230 channels to connect all individual probe elements at the same time. Zetec's high-end dyne array is one of the rare standard commercial systems to offer this capability. This slide illustrates the mechanical inspection sequence for the detection of circumferential flaws. The probe pan will be moved according to a multiple line sequence with a scanning movement parallel to the weld and large increments perpendicular to the weld. For all probe assemblies, the beam orientation is perpendicular to the flaws that we want to find. For detection of actual flaws, the probe pan is rotated 90 degrees, again to obtain a beam orientation perpendicular to the flaws that we want to find. The multiple line sequence will now have a scanning movement perpendicular to the weld and large increments parallel to the weld. After clearly defining the inspection techniques, we have also determined the extent and the resolution of the scanning sequences to obtain full coverage in accordance with the code requirements. Let us now try to quantify the performance of the system in terms of inspection speed. At this time, I will consider a vessel weld with a wall thickness of 200 millimeters and a circumference of 16 meters. For the examination volume, we will consider the width of the weld and a ½ inch extra on either side of the weld, just like we saw on the various slides in this webinar. During practical trials in our laboratory, we have confirmed that for scanning sequences, including all probes for either circumferential or axial flaw detection, an acquisition rate of approximately 20 Hz, meaning 20 complete acquisition cycles per second, can be supported by the dyne-array system. For detection of circumferential flaws, when using a scan resolution of 2 mm, a scanning speed of 40 mm per second, roughly 1.5 inches per second, can be achieved. The net scanning time for 2 meters of weld length would be less than 10 minutes. The component will be installed on power rollers, so it will have to be rotated in between scanning sequences, and this may take some time. Still, completing the 8 or 9 sequences that would cover the full weld length should take less than 5 hours. For axial flaw detection, when using a scan resolution of 2 mm, a similar scanning speed of 40 mm per second can be achieved, and the net scanning time for 2 meters of weld length would be less than 5 minutes. So the complete weld, including turning of the component, data storage, and setup change, would take less than 3 hours. In total, in nominal inspection conditions with well-trained operators, we are confident that the inspection of a typical vessel weld could be completed in one shift, meaning 8 to 10 hours. The old inspection technique with industrial radiography takes longer and is disruptive to other activities around the component. So the mechanized UT inspection represents a considerable time reduction of the total process. As I mentioned before, there is great value in ray tracing and acoustic beam simulation to support inspection technique development. But this theoretical work needs to be complemented by experimental evidence. So to further illustrate the inspection capability of the system, let us look at the results of some practical trials that we performed in our laboratory. We used a carbon steel welded specimen with a wall thickness over 200 millimeters, representative for a nuclear vessel weld. The specimen has a double J weld of approximately 35 millimeters wide and contains the following flaw types: cracks, lack of fusion, lack of penetration, and inclusions. The specimen also contained some unintended flaws. In addition, there are data from a dedicated specimen with inserted artificial flaws for quantitative assessment of the sizing capability of the TOFD technique. We will use the UltraVision Classic software to review the data and take the opportunity to show some of the advanced analysis tools. Since the inspection system is capable of collecting the signals from all probes simultaneously, all data from a part of the weld will be recorded in a single data file. We can see the different channels in the UltraVision Manager and can observe the presence of the linear and sectorial phased array UT data groups. During our laboratory trials, the TOFD data were collected separately for practical reasons. This screen layout shows the raw data from the sectorial scan used to cover the mid and far surface regions for circumferential flaws. The blue horizontal axis represents the scan axis along the weld. The green axis represents the index axis perpendicular to the weld. We have the following views on the screen. Top left, we see the weld cross-section showing the UT data relative to the weld bevel. Top right, we have the weld front view showing the indication depth, the purple axis and the position along the weld. The view below right shows the weld top view, and finally the A-scan signal linked to the data cursor is shown below left. By moving the data cursor and the angle cursor, we can scroll through all the data of the considered channel. And we can do the same for each channel. For instance, the electronic linear scan at 70 degrees shear wave, which is used to cover the near surface region. You can imagine that for this type of inspection, analyzing the raw data would be a time-consuming process. The volumetric merge tool in UltraVision Classic allows us to drastically speed up the process while maintaining the reliability and the precision of the analysis. The detailed definition of the various merge operations can be prepared in advance and rapidly imported during data analysis on site. The merge tool allows the analyst to import and execute all operations by selecting a file, as we can see here. Basically, the tool creates merged data groups containing in each volume unity of the weld the maximum amplitude amongst all the channels considered in the merge. The data analyst will merge all channels or a subset of channels according to his data analysis procedure. It is very important to mention that the volumetric merge tool does not replace or alter the raw data. It's just creating additional data groups. This screen layout for the merged data is organized in a very similar way as for the raw data. We're now looking at merged data that contains signals from linear and sectorial scans for one probe orientation, roughly 110 focal laws. Using the projection cursors, the analyst can now very easily isolate and visualize every individual indication in the different regions of the weld. For instance, some inclusions in the near surface zone, or a lack of penetration in the far surface zone. You can observe that the welded specimen also contains some flaws at depth higher than 200 millimeters, some with low amplitude. The 16-bit amplitude resolution on the Dynray system allows the analyst to use the soft gain tool for better detection of flaws with low amplitude responses, without the need for rescanning. By using the palette tool, we can see that the indications have a very good signal-to-noise ratio. They were, however, not taken into account for our quantitative conclusions, since the inspection technique was optimized, in this case, for a 200 millimeter thick weld. We will work on the merged data group that contains the phased array pulse echo signals from all probes and all orientations to illustrate the detection results. The indication table in UltraVision provides the tools for an efficient analysis process of the individual ultrasonic indications. The analyst just has to draw a contour around the region of an indication, then click to add the indication, and the software will automatically list all quantitative information about this new indication in the existing table. The information fields can be selected from a wide range of standard parameters, including amplitude, position, and length of the indication, but also the name of the data file and the data group that contain the indication, and the date when the file was collected. In this case, special information fields were prepared through Excel to calculate and record the amplitude of indications compared to the DAC reference level. All this ensures efficient analysis while minimizing the risk for human error and maximizing the traceability of the data. When all indications in the examination volume have been boxed in and saved in the indication table, the analyst can zoom in and review any indication in detail, just by double-clicking on the corresponding line in the table. The quantitative information will be saved with the data file upon closing it. Also, the indication information can be exported as a text file that can later be imported in either Excel or a dedicated database. As mentioned before in the webinar, formal detection and reporting of indications will be based on amplitude level relative to a DAC curve. When applying a -20 dB threshold using the palette tool, we can see rapidly the result of this detection procedure. In addition, we can observe that the merged data show a high signal-to-noise ratio, actually above 20 dB on all intentional flaws in the welded specimen. We have done all the data analysis considering a flat geometry. But UltraVision Classic also supports visualization in a 3D environment. I used embedded UltraVision tools to create a CAD model of a cylindrical ring containing a weld similar to our test specimen. The operations required to generate a full 3D image of the phase array inspection data are very similar to the volumetric merge. Very similar to the projection gates in the 2D views, we have the cutting planes in the 3D views to visualize a specific region in more detail. The 3D representation of the data will be very useful to accurately plot data from actual flaws in smaller diameter vessels, and of course for nozzle inspections, but that last topic is beyond the scope of this webinar. After the detailed analysis of the pulse echo phase array data, let us now take a quick look at the results of the TOFD technique. UltraVision also has the dedicated tools to efficiently visualize and analyze TOFD data. On this slide, we see data taken on the same welded specimen in a typical display layout for TOFD. We see the unrectified A scan on the left and the B scan on the right. When zooming in, we observe that inclusions, lack of fusion, and a crack between 130 and 145 millimeter depth are clearly confirmed with the phase array TOFD technique developed for zone Z3. We also performed phase array TOFD scans on a specimen containing embedded alumina inserts. These are very thin defects that do not generate specular reflections like can be observed on EDM notches. The behavior of the alumina inserts is very close to the behavior of a real crack. The specimen contains several identical inserts of 4 millimeter high and 40 millimeter long. Again, I'm showing signals from the phase array TOFD technique that covers the zone Z3. First of all, we can notice a good signal-to-noise ratio and a clear discrimination of the tip and bottom diffractions. This allows for accurate length and through-wall sizing. Using the dedicated TOFD cursors, we measure in two cases the correct height within a 0.2 millimeter tolerance and the correct length within 1 or 2 millimeters. This concludes the analysis of the ultrasonic data from our experimental laboratory trials and the validation of the proposed inspection techniques. From all the information presented in our webinar today, we can draw the following conclusions. Zetec's industrial data acquisition system and laser-guided inspection robot allow for fully mechanized and efficient UT examination with phased array and TOFD on a large range of thick vessel welds after manufacturing. The inspection is performed from the OD surface. The Dynaray high-end phased array system can simultaneously run all probes for a total of 230 channels and collects data from all focal laws and TOFD pairs for a given flaw orientation, either circumferential or axial. For each part of the weld length, 2 scanning sequences will be sufficient to cover all flaws. Based on the proposed inspection techniques and scanning sequences, we have quantified the performance of the system in terms of inspection speed. The characteristics of the Dynaray system allow to perform a full thickness inspection of circumferential narrow gap welds up to 200 millimeters thick in 8 to 10 hours, which results in a considerable time reduction of the global process. I have illustrated that the UltraVision Classic software provides the required tools for inspection technique development and for an efficient inspection workflow, including setup, calibration, inspection, and data evaluation. Experimental validation on representative test specimens with realistic defects has shown excellent results with both pulse echo phase array and TOFD. Typical welding flaws in a thick vessel weld are well detected by pulse echo techniques with a signal-to-noise ratio of more than 20 dB. In addition to detection confirmation, the TOFD techniques provide accurate length and through-wall sizing of crack-like defects. And finally, in addition to our best-in-class products, Zetec can provide industry-leading expertise on manufacturing inspection of critical vessel welds. This concludes the presentation part of the webinar. We will now take some time to answer a few questions that we have received since the start of our webinar.